Good afternoon. My goal today is to wrap up basically our discussion of Newton's laws. We're not going to be done with him. He's going to inform what we do all semester. But I do want to start getting into some other topics today. So we're going to try to wrap up Newton's laws. In particular, Newton's third law, which I've already mentioned, I don't think we got into quite as much as I'd like to. So I just want to get back to Newton's third law just briefly, then we're going to do some other stuff. Here's Newton's third law. Again, stuff pushes back. I've already mentioned that, but I just want to make sure we all believe that and have internalized that to some degree. The easiest way, I think, to see that, I'm going to need a volunteer for. There. Okay, there's whoever wants to come up here first. Sure, you're closer. Sorry. Okay. Great. Thank you. I think hopefully everyone can see. I might zoom in. Let's see. Let's try. That's a little more zoomed in. Okay. Let's see. We're going to try to get on camera here. There. Okay. Here's the demonstration. Can you hold one of these, please? Thank you. Hold it like that so everyone can see the numbers. There we go. Okay. So hopefully everyone can see the numbers here. So what I'm holding here, what we are holding here are scales that measure force, measured in newtons. They named the units of force after the guy, Newton. So this is measuring force in newtons. And the weight of the thing kind of balances out. I got 0 here. So yeah, if you turn it upside down, it goes negative. Yep. Okay. So here's the demonstration. We're going to push on each other, or I'm going to push on him, or he's going to push on me. I forgot your name. Billy. Billy's going to push. Billy's going to push on me. He has better shoes than I do, and he looks bigger than me, so I might go this way. But here's the demonstration. We're going to push on each other equal and opposite. We don't have any way around that. That's just the fact of physics. And so let's start by, you just hold yours still. Actually, I'll hold mine. I'm just going to stand here I'm not paying attention. Now, you go ahead and push on mine. I'm not doing anything. Let's see. Let's get so they are. All right, right now they're reading both about 70. Right now maybe around 80. So if you look at the numbers, they're both around 70 or 80. He's doing the pushing. I'm just standing here. I'm minding my own business. I'm not trying to push back equal and opposite. But no matter what he pushes on, or what the two scales do, notice they always move in tandem. So you could even start accelerating me, start pushing me this way. And notice they'll stay in tandem. They'll stay together. Now, they're kind of going all over the place, but hopefully you can see that. So whether I was just standing here minding my own business, or now you're standing there minding your own business, and I'm pushing on you, right now they're both 90, they're both 80. So it doesn't matter it doesn't matter who's being intentional about it, who's doing the pushing, who's the one minding their own business, who's maybe accelerating. Let's try this. Let's put just one of us on one of these things. Let's do you want to? I can do it. Unless you want. All right, go for it. All right, hop up on there. Okay. So let's see. We'll go this way. Don't fall over. Don't die. So flip it around so we can all see it. This thing. Yeah. All right. So now I'm going to reduce his friction. So he doesn't have. Speaking of things pushing back, he doesn't have the floor pushing back on him. And so really his net force will essentially be what I push on him. And so again, here's a situation where I'm doing the pushing. He can't push back. So maybe he'll get all the force because I'm the one doing the pushing. But even though he has almost no friction pushing back on him, he's standing on a wheeled cart, these two numbers should still read the same, even though I'm accelerating him away. Whoop. They moved, hopefully you saw that they moved in tandem. So I'll slowly accelerate you back here. Okay. So there we are. Okay. So even though he doesn't have anything to push back, I'm the one doing the pushing. You see that we're pushing on each other equal and opposite. Those two needles move in tandem. There's no way around that. And then we could do it with two of them. Let's see what happens now. And so let's see. Now neither of us has much friction. And so now we're both going to experience the same force equal and opposite. Neither of us have the floor, which is that external agent holding us in place. Neither of us have the floor holding us still. So we're both going to accelerate from one another. We'll experience the same force, and now we get to see who's heavier because the more massive person will move less. There. I think I was I was the one doing most of the accelerating there. But hopefully you saw that our force needles moved in tandem. I'll try that a little more slowly. So let's see. Our force needles are equal no matter what we do. And the more massive person or maybe the better person with more friction in their bearings or something is going to be, okay, there's that move. Okay. Let's try the, let's see. If you can push on me and I'll just pretend I'm minding my own business. And I think you saw they move together. It was quick. Okay. Any questions about that? Great. Thank you very much. Nice. Okay. That brings us to our iClicker for the day. And while we're all getting our iClickers out and our app fired up and everything, let me just mention tomorrow night during office hours, I'm going to sit down and go through all the iClicker emails I've gotten and try to sort all the grades out. I've gotten a lot of iClicker emails. So wait till tomorrow night before you think I'm ignoring you. And speaking of office hours tomorrow, office hours are normally here in the physics building from 5 to 7. I need to shift that 45 minutes, so it's going to be 4:15 to 6:15 tomorrow. That'll be a one-time thing, I hope. But I just need to shift it like 45 minutes, so it'll be 4:15 to 6:15. Okay, hopefully we've got our iClickers out and ready to go. Here's our first and maybe only iClicker question of the day. And it is, if we took everyone on the planet, all of us, and we all stood shoulder to shoulder, how much space would we take up? It's not in your notes. Just a guess. This is one of those ones. Another note about iClickers. I've had people ask me, how in the heck was I supposed to get that was a zoomed in picture of a staple? Don't mark me a minus on that one. Most iClicker questions in this class, it turns out, are random like this, and if you try, I give you credit. So okay, I might eventually get to an iClicker question where I expect you to know the answer. This one is a tough one. But that's if I actually expect you to know it. So you get 100 if you just guess. Yeah. Yeah. I do not expect you to know this one. All right, let's take 30 more seconds. Looks like the votes are grouping around people that think you're going to need a lot and people that think you're going to need not that much. All right. 10 more seconds to lock in your vote. We good? All right. There's our guesses. So I did not expect you to know the answer to this one. I did expect you to, well, I don't know. Yeah, I did expect you to try to go through maybe what's sometimes called an order of magnitude calculation and think, okay, there's like 7 billion, I don't know if we're up to like 7.5 billion people on the planet. Shoulder to shoulder means that maybe everyone gets 1 square meter. So maybe if we had 7 billion square meters, that's how big it would need. 7 billion square meters. Square root of that, tell you how big the square would have to be that we would all fit in. Turns out you can take every person on the planet. It's a big planet, and it's pretty crowded. I don't know if you've heard. There's some very crowded areas. But actually, we could cram everyone into LA. We could cram everyone into LA. Now, LA is huge, by the way. So it's not, Charlottesville wouldn't do it. LA is very, very large. But if a rough order of magnitude calculation, we could fit everyone into LA, shoulder to shoulder. Everyone on the planet. I think that's kind of nuts. I was a little bit surprised when I actually started doing the math, and I'll tell you why I started doing that math and what this has to do with Newton's third law. But I decided I want to see if where everyone would fit. And my first guess was like Texas or something. I started doing the math. I had to double check my numbers because that seems crazy. I would be surprised if we could fit everyone in the United States into LA, much less everyone in India and China into LA. But it turns out 1 meter squared is about all. That's about all we need. Now here's what got me thinking about that question. Here's why I asked that question of myself. Where could we fit everyone? I was wondering if we could fit everyone into a relatively a spot. And if this is the world, like I said, LA is huge, but LA is basically just a dot on if this is the world. So we actually could fit everyone on the planet. If we could get all the boats and planes that we have and just ship everyone onto one spot, we could all stand here. Here's why I wanted to know that. I wanted to know Newton's third law stuff pushes back. So right now, the force you're experiencing holding you into your seat, right now you feel that thing pushing you in your seat, that's your own weight. That force you're feeling between you and the seat, that's your weight. That's a mutual force. And I've already mentioned that. Newton's fourth-ish law says force of gravity equals gmm over r squared. It's a mutual force. Both you and the earth are feeling that force. So right now, the earth is pulling me down with 170 pounds of force. I am pulling the earth up with 170 pounds of force. The earth feels a sizable tug due to my presence. 170 pounds, that's a lot of force. I mean, do a pull-up, that much force, you're pulling on the earth all day long. And multiply that times 7 billion, and we're all a pretty big chunk of mass, all 7 billion of us. Take everyone in this classroom and multiply that by 500 million or something like that. There's a lot of us. And so I thought, okay, first of all, does that add up, just us standing there? What if we all stood in one spot? Would we like squish the earth or something like that? Would the earth like come up closer to us? And then I thought, what if everyone, all 7 billion of us, we coordinated, we said, ready, 1, 2, 3, and we all jumped. Could we like shoot the earth off into space in the other direction, or maybe at least alter its orbit or something like that? And the answer is yes, we can affect it, because Newton's third law, stuff pushes back, always holds. As I hopefully demonstrated up here a second ago, there's no way around that. I push on you, you push back on me. If I push on an air molecule, it pushes back on me equal and opposite. Air molecules have the ability to do that. If I push on another person, whatever. If I push on the earth, it's going to push back on me equal and opposite. And so maybe if we all 7 billion of us gave a good jump, we could move the earth. Maybe that should have been the eye-clicker question. If everyone on earth stood in one spot and just gave a really good jump, how far would the earth go? Question A would be, I don't know. A would be the answer. It would be, I think it turned out to be less than the diameter of a hydrogen atom. It was very, very, very depressingly small. It would be pretty much a waste of time. Fly everyone up to LA and get them all crowded in there, and then it would not even be detectable. And so yet another perspective on our Earth. It's quite large. A 6 with 24 zeros after it large in mass. So it's very, 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 very massive. Okay. Any questions? All right, I want to shift gears a little bit. A guy named Richard Feynman, who you may have heard of, he died, I think, in the 90s. Was a scientist at Caltech, renowned scientist. He's put up there in that echelon of scientists with Einstein, people that just came along and gave us a leap in our understanding of the world. I think right now as we speak, this building is full of physicists doing really hard, good work, trying to make a little nudge in our understanding of the universe. And every day there's real scientists all over the world making little nudges in how much we understand about the world. And then every now and then the world gives us a Fineman, and all of a sudden that leap is significant. And so physicists in this building, physicists all around the world, use Feynman's understanding of nature. They even used some of his techniques for just how he liked to draw diagrams. Everyone picked up the way he draws diagrams. Everyone does that now. And he actually, I remember, I think I was in undergrad when, I remember one of the problems we did in physics class was an order of magnitude calculation about, it was a problem that Fineman had dreamed up. And it was, if you had all of the protons and electrons you have right now, so you and I are made of protons, neutrons, and electrons. And he said, if you just had 1% more electrons, so take your current number of electrons, just bump them up by 1%. And then your friend did the same thing. So you've got all these protons and neutrons, like, so you know that you're mostly water, you're mostly carbon and hydrogen and oxygen. Take all those electrons, just bump them up by a little bit, 1%, and your friend did that. And you stood 1 meter from each other. The electrostatic repulsion, in other words, the electrons push, two negatives repel. You guys would repel each other with the weight of the Earth. And the problem is to go through a quick order of magnitude calculation. Okay, I'm 70 kilograms. That's 70 moles of atoms or something. That's how many protons I have, and that's how many electrons. You do the math, and boom, all of a sudden you realize how amazingly strong the electric forces are. So the force that, binds you together, but also is that force that you can stick balloons to the wall, or that force that you can shock people in the wintertime, that thing. Anyway, so Fineman gave us a good order of magnitude calculation to understand that. I'm also going to use Fineman to move us into the next chapter for this class. Before I do that, let's see. Before I do that, let's quickly review a physicist's view of the universe. Here's a physicist's view of the universe. I typed up a slide that I hope everyone can read, even from the nosebleeds. But here's how a physicist these days tends to think of the universe. The universe is kind of two things. It's stuff, that's matter, that's me and you, and it's the interactions between those bits of matter, or sometimes called the forces. I also sometimes like to think of this as the nouns and the verbs of the universe. The universe is basically some nouns and verbs. It's stuff, matter, particles, you and me, and the things that cause those things to interact. Or another way to put it is just the information that we even exist, that I'm here and you're there. So the thing that lets us interact. So that's kind of how a physicist today working in the world understands the universe. So there's stuff, and then there's the interactions between that stuff. So by stuff, I mean matter. Everything you know of is made of matter. Tables and paper and notebooks and computers are all matter. Plastic chairs, paper, people, that's all what I call, what we call matter. That's stuff. It's protons, neutrons, and electrons. Sky and air is matter. Stars are matter. I don't know, you name it. That's matter. Oceans, rocks, trees, it's all matter. Now, just as a side note, I put a little asterisk up there. If you want to feel a little bit, hopeful or depressed, depending on your perspective, about our understanding the world, it's the fact that I think we should feel very hopeful and excited and proud that as a species we've figured out matter pretty well. We've done a really good job. We think we may have it's possible we may have found it all in terms of what it's all made of. We think we might know. So that picture might actually be pretty complete. So good job, us, we did it. Here's the slightly depressing part. Our current understanding of the world is that stuff called matter that you and I are familiar with, like hydrogen, helium, carbon, all that stuff, probably makes up about 5% of the universe. The other 95% is a mystery. So if you're still trying to figure out what major you want to go into, there's a room in physics. We still call the other 95% of the universe dark because it's basically a sector of the universe we don't even know what it is. We have a label for it, and that's about all we have. We don't know what it's made of, how it behaves, why it's there, how it got there. There's this stuff 95% of the universe. I'm not making that up. It's just we don't know. So the matter stuff, we've got that down. We know why apples fall out of trees. We know why basketballs do what they do. So go us. We got 5% down. We got a long way to go as we look out in the universe. It appears to be that there's 95% that we don't know about. Question? Great question. How do you know that you don't know? How do you know? And we actually know pretty precisely how much we don't know. Like it's down to, we've got it down to like 2 decimal places. Like we know really well 5.12% of the universe. How do you make that kind of precise statement about how much you don't know? And it's basically that we've gotten really good at making observations. We got really good instruments. We got really nice telescopes and computers. And our telescopes and computers and measurements and data and experiments all reveal a universe that is behaving not even close to how it should behave if the 5% was that, if that was it. So make up a universe with just matter. Make stars out of matter, which they are, make planets out of matter and people, and get them all going. And it wouldn't even behave remotely like it does. Just take our galaxy, for example. Hopefully everyone knows that we live in the middle of a galaxy called the Milky Way, and it's lots of stars all spinning around. It looks like a disk. That Milky Way would just fly apart if it was just made of matter. And so what we do is we then make models. Okay, in the computer, we make a computer model. What would keep the Milky Way from not flying apart? Well, if it was 95% other stuff, or if it was like 87% other stuff, that would do it. So in order to make what we see in the universe make sense, we have to inject like 87% other stuff just to keep it together. Because most galaxies are doing this, and they would fly apart if that wasn't true. And then the universe also is expanding. I don't know if that's common knowledge, but when we look out and when we look at other galaxies, they're all moving away from us. So the only explanation that everything we look at is moving away from us is either the universe is we are stationary and we just happen to be dead center, the sort of pre-Copernican view of the world. We're in the center and everything just happens to be moving at a velocity. Or the other way to look at it, how can everything be moving away from each other, is everything's expanding. So no matter, imagine if this room just were growing, me and you would be getting further apart. And you'd be getting further apart from your neighbor, and you'd be getting further apart from the person in front of you and behind you. That's our current understanding of the universe, is that we're all moving apart from one another right now. Space itself is growing, and so the space between me and you is actually growing. And that fits our observations. But here's the super weird part that accounts for that other unknown part of the universe, and that is it's accelerating. And so not only are you moving away from me, you're moving away from me at an increasing rate. That makes no sense according to the physics we currently know. So nothing, as I've been saying for a couple weeks now, nothing accelerates without a force. Well, everything's accelerating. So there's a kind of a pervasive force in the universe that has to be strong enough to be accelerating galaxies at ridiculous rates. No idea what that is. I mean, literally no clue. And so, yeah, that's where we are in the world of physics right now, is we really nailed down some stuff. And there's some other stuff that we're like, I don't even know where to start studying that. Yeah, question? Yeah, great question. So the question is, but the galaxy is made of stuff, and stuff is attractive. And so, but stuff, if you remember, that attractive force falls off with r squared. So in order for two things to attract each other in this universe, they have to be pretty close. So in the grand scheme of things, we're pretty close to the moon, and we're pretty close to the sun. So we've got this little neighborhood called the solar system, and everything's kind of attracted, which is nice. But that is actually attracted to the center of our Milky Way. So we're actually orbiting the Milky Way. So, the moon orbits the Earth orbits the sun orbits the center of the Milky Way. And that's all attractive. That's gravity. We can explain that okay. But we're so far from the next closest galaxy that all the mass and all that mass, it would take, we're too far. So we're not going to attract each other. Now, some galaxies are close, and they do start orbiting each other and eventually collide, and cool stuff happens there. But for the most part, the universe is just doing this, which would make sense if there was a Big Bang. Now we're all doing this. But we're doing this at an accelerating rate. It just doesn't make sense. But that's what we observe. So here's the room in physics. Like I said, if you want to change your major, someone needs to either show that all our understanding of physics is wrong. That's why our observations seem crazy. Or there's 95% stuff that we're not accounted for. So one of those two things is probably true. There's a bunch of stuff out there doing the things that we can't explain, or our understanding of physics is so wrong that explains why the discrepancy. Either way, there's a bag full of Nobel Prizes waiting to be won for all that stuff. Okay, so that's the 90. Let's get back to the 5% we're good at. That'll get us pretty far. I mean, because the 5% we know, I mean, that is, like I said, that's everything. I mean, that we encounter. So your whole life, all the cell phones and cars and oceans and Cocker Spaniels you'll ever encounter are all made of matter. So that's pretty good stuff to know. So, I mean, like I said, it's not like, oh, geez, we don't know anything. We know we're good at that stuff. So let's get back to that. Okay. So I think the physicist's understanding of the world is that there's stuff and then there's the forces. That's pretty much how we understand it. In this class, how I'm going to kind of divide our topics, we're going to try to understand the moving bodies parts of the universe. And so we're going to try to understand, people and cars and tennis balls and basketballs and bowling balls and, I don't know, even planets and moons and car keys and things like that. So the moving bodies parts of the world. That'll get us pretty far. And then I do want to we're going to spend maybe like the last third of the semester on what you could call the invisible stuff, and that's just like radio waves and microwaves and cell phone signals and text messages and things like that. Light. That's a big enough part of our world, especially in 2016, that's worth studying. So how do cell phone signals work? How does Wi-Fi and Bluetooth work? I think that's a good thing to study. So that's kind of where we're going to go. Now, up till now, we've been understanding the moving bodies by Newton's laws. That's how we understand moving bodies. So as I've said, and this is true, if you want to get something going, you have to push on it. Or if you observe something changing its state of motion, accelerating, speeding up, slowing down, or taking a left, there was a force, F equals ma, all that is actually sufficient to describe our universe. So I should say that. So what we've talked about so far this semester, Newton's laws, is sufficient to understand what's going on in the universe. However, what I'd like to do over the next couple of days is look at two other ways of looking at the universe. So I have to stress, there's not parts of the universe that obey Newton's laws and parts that don't. All of the universe obeys and is understandable through Newton's laws. That said, there are other approaches or other frameworks or other lenses that make the world more understandable. And so we're going to start talking about a couple of those. And a good example is I've got a bowling ball tied to a string in the room right now. And if I were to let that bowling ball go, it's going to swing like a pendulum. And the forces acting on that are pretty difficult to understand, because the weight of the ball is always straight down. So as it moves through its arc, its weight is always going to be straight down. The other relevant force on that ball is the tension in the rope, the cable. The direction of that is going to keep changing. So right now it's kind of up and to the left. At the bottom of its swing, it'll be straight up, and the top of its swing, it'll be up and to the right, and that's going to keep changing constantly. So if I were to try to understand what's going on in that situation, it's going to be very difficult using only what we've talked about so far this year, Newton's laws. Now, definitely doable. If we had no other approaches, no other lenses, we'd be fine. It works. You'd have to use some calculus to integrate the angle and the force. I don't want to have to get into that. So what we have is other frameworks that are better for understanding the universe. In fact, there are some parts of the universe that Newton's laws just get too out of control that we definitely don't want to go down there. And we physicists just use the other frameworks because it would take a supercomputer to use the other framework. So today we're going to start talking about energy, which is one of our other frameworks. And to get us to energy, I'm going to use Richard Feynman again. And I'm going to read you guys a story. Because I have this book called 6 Easy Pieces. And it's supposed to be 6 of the easy things that Feynman told us. None of them are easy, but I'm going to try to take his word for it. So these are the 6 easy things that he left to his physics students. So there's Feynman right there. So he was a professor at Caltech. He had he has, I think, 1 Nobel Prize. He also worked on the Manhattan Project. And then also interestingly, when the Challenger blew up in the 80s, I think it was, they just called him. They said, okay, NASA called him and said, Challenger blew up, we can't figure it out. You're the smartest guy on the planet. So I don't know if we have one of those right now. I guess Stephen Hawking maybe. But just that guy you call when you can't do your homework. We got to call Feynman because we cannot figure this out. So they called him and he figured it out. He figured out it was the O-rings, I think, were contracting in the cold weather, if I remember right. So anyway, I'm going to read you guys a story. This is Richard Feynman describing energy to his class, and I think he does a good job with it. So it's like 2 pages. Here we go. So this is what Richard Feynman asks you to do if you're going to try to understand energy. He says, imagine a child, perhaps Dennis the Menace, who has blocks, which are absolutely indestructible and cannot be divided into pieces. His mother puts him and his 28 blocks into a room at the beginning of the day. So he has 28 blocks. At the end of the day, being curious, she counts the blocks very carefully and discovers a phenomenal law. No matter what he does with the blocks during the day, there are always 28 at the end of the day. So she has discovered a sort of a conservation law. This continues for a number of days until one day there is only 27 blocks remaining. But after a little investigation, she sees that there's one under the rug. So she realized she must look everywhere to be sure that the number of blocks has not changed. One day, however, there appears to be a change. There are only 26 blocks. Careful investigation indicates that the window is open, and upon looking outside, the other 2 blocks are found. Another day, careful count indicates that there are 30 blocks. This causes considerable consternation until she realized that Bruce came to visit, bringing his blocks with him, and apparently left a few at Dennis's house. After she has disposed of the extra blocks, closed the window, doesn't let Bruce in, and everything is going all right until one day she discovers there's only 25 blocks. However, there is a box in the room, a toy box, and the mother goes to open the toy box, but Dennis the Menace screams, "No, you may not open the toy box." So the mother is not allowed to open the toy box, but being extremely curious and somewhat ingenious, she invents a scheme. She knows that the blocks each weigh 3 ounces, so she weighs the box at a time when she sees all 28 blocks present, and it weighs 16 ounces. So the next time she wishes to check, she weighs the box again, subtracts 16 ounces, the weight of the empty box, divides by 3, and that gives her the number of blocks in the room. So there's her equation. There's her equation. Number of blocks that she sees, plus this equation she came up with, this term she came up with, weight of empty box, weight of the box, minus the empty box weight, divided by 3, tells you how many blocks. Add that to number C, and you've got a constant. That constant is 28. Okay. Then there appear to be some new deviations, but careful study indicates that the dirty water in the bathtub is changing level. The child is apparently throwing blocks into the water, and she can't see them because the water is so dirty, but she can find out how many blocks are in the water by adding another term to her formula. Since the overall height of the water was 6 inches, and each block raises at 1/4 of an inch, her new formula is that. The number of blocks plus the number in the toy box plus the height of the water minus the height of the water if there weren't any blocks in it, divided by the height that each block raises the water, and then we've still got a constant 28. In a gradual increase in the complexity of her world, she finds a whole series of terms, each representing ways of calculating how many blocks are placed where she's not allowed to look. So you can imagine this process goes on. There's a number in the toy box, the number under the rug, the number in the bathtub, and she has formulas for each one. As a result, she finds a complex formula, the quantity of which has to be computed, but it always stays the same for her situation. So what is the analogy with energy? The most remarkable aspect that must be abstracted from this picture is that there are no blocks. Take away that first term, number of blocks, take away the first term, and we find ourselves calculating more or less abstract things. The analogy has a few points. First, when we are calculating energy, Sometimes some of it leaves the system and some goes away, like when they threw some out the window or Bruce brought the blocks in. Sometimes some goes out, sometimes some comes in. In order to verify the conservation of energy, we must be careful that we've not put any in or taken any out. Second, energy has different forms, and there's a formula for each one. There's gravitational energy, kinetic energy, heat energy, elastic energy, electrical energy, chemical energy, radiant energy, nuclear energy, mass energy. If we total up all the formulas for each of these contributions, it will not change except for energy going in or going out. It is important to realize that in physics today, we actually have no knowledge of what energy is. We do not have a picture that energy comes in little blobs of a definite amount. It's not that way. However, there are formulas for calculating some numerical quantity, and when we add it up, it always gives us 28. Always the same number. It is an abstract thing in that it does not tell us the mechanism or the reasons for the various formulas. Okay. So that's Richard Feynman describing energy. And I think that's a very useful tool or very useful picture when we think about energy in this world. So that is exactly how I like to think of energy. And there's I'll reiterate a couple of the points he makes. First, we don't know what energy is. It's an abstract quantity. We calculate it, but there really is not, that first term isn't there. So when I add up all the energy in this room, I've got a bunch of formulas. The number of people and the whatever, I can add up all the energy in this room, but it's just a computed quantity, and it's very abstract. So I don't hold energy in a bottle. I don't have energy anywhere. I can have thermal energy, mass energy, gravitational energy, all these different types, but they're all calculated and it's very abstract. So why would physicists hinge a lot of their understanding of the universe on such an abstract quantity? Because it appears to be conserved. Because it's conserved, we can use the calculations to understand how stuff happens. And so in other words, I have a system, and I don't know what energy is, but I do calculate that it's got 28 of them. Whatever those things are, that abstract quantity, I calculate 28. And I make sure that no energy goes in or out. I can be sure that it's got 28 later. So then when I calculate, let's see, here's some of the energies that Feynman gave us. So I calculate my box has 28 of thermal energy. Later, I calculate it has 24 of thermal energy. 4 went away. But if I can trust that energy is a conserved quantity, you may have heard you cannot create nor destroy energy. If I trust that it's a conserved quantity, those 4 must have gone somewhere. And that can help me really understand the universe when I look at the universe and I just constantly am doing my accounting of where my energy is and what type it's in. So in fact, in particle physics today, that's largely how we do a lot of our experimentation. We watch energy just go away, and then we can make very precise measurements of how much went away, and then we can make conclusions based on how much went away. So we trust that it's a conserved quantity, and so when we see our numbers change, we can start drawing conclusions from that. I know it's conserved. I know I have to have 28, so where'd it go? And some of the crazier experiments, like at the Large Hadron Collider at CERN, they're hoping to see some just go away. And that will reveal, that'll be good evidence for the existence of extra dimensions. I'm not making that up. Physicists, again, if you're wondering what your major should be, there is this major called physics where there are people that spend their day worrying about time travel, extra dimensions, negative gravity, black holes, dark matter, dark energy, antimatter. It's some pretty fun sci-fi stuff. So there are theories that sometimes if we do see energy go away at a specific time and a specific amount, could be good evidence for another dimension, and which I think is pretty cool. Okay, so here's a bunch of them: thermal energy, chemical energy, all those that are up on the board, even including mass energy, which I think next class we'll get into a little bit. But yeah, so there's the utility of energy as a concept. It's abstract, it's just a concept, but the utility is I have formulas for thermal, I have formulas for chemical, I have formulas for electrical, and that can help me understand the situation. So a sort of quintessential demo is I'm going to swing that ball, and if I trust physics that energy is a conserved quantity, then I'm just going to watch that ball go through a couple transitions of energy type. Now in this class, in this class, we're going to be concerned mostly with 4 of those. So you saw on this list, I've got chemical, radiant energy, nuclear energy. We're not going to get into those much. But especially for the next couple days, we're going to be concerned mostly with two types of potential energy, and we'll talk more about what that means, but just quickly, it means stored energy. Two types of stored energy and two types of kinetic energy. Kinetic meaning motion. So two types of energy motion, two types of potential. So a quick representation or a quick example of that is right now, that ball, that bowling ball, that red bowling ball, is above its lowest position. If I were to let it go, its lowest position is like right here. Here's its lowest position. So it's actually above its lowest position. It has, because it's above its lowest position, this is like the definition of gravitational potential. If it's above its lowest position, it has potential energy. When I let it go, it's going to move to that lowest position. So its potential energy decreased. According to the conservation of energy, you can't do that. You can't go from some energy to no energy. Let's call this 0 down here. So it's right now it's above 0 and it goes to 0. Where did it go? Well, it had to have gone somewhere. And this is one of those situations that energy is a useful tool rather than Newton's laws to help me understand what's going to happen. What's going to happen is that energy is going to go away. So when it gets here, it's gone, that potential energy, gravitational potential. So then I can start asking, where did it go? And I can go through my list. Did it go into thermal energy? Did it go into radiant energy? Now, if I see that thing getting really loud, if it starts making a lot of noise, it went into acoustic energy. If I see it start glowing brightly, I know it went into thermal or radiant energy. Probably those won't happen. What else is on my list? If I see it start attracting metal, it's got into magnetic energy. If I see, whatever. Probably where it's going to go is into kinetic. So I think I can already predict, and energy is also a useful tool for prediction. I can predict where that energy is going to go. It's going to lower its potential. It's going to go into kinetic, the energy of motion. Now here's another reason that's useful. I can, as a predictor, as a prediction, I can, that's a little better view of what we're looking at. I can predict that no energy will be added to the system. So when I let go of that ball, if no work is being done on the system, and that's where, in the analogy of the blocks, she comes over one day and it went from 28 up to 30 because someone added blocks to the system. If I'm careful to not add energy to the system, I can be sure that whatever I start with is what I end up with. Hopefully I can trust that. So if I were to take this ball, let's just give it a shot. Right now it has a certain amount of potential energy. I'm going to let it go, and it's going to swing down here. It's going to get to its lowest potential state and highest kinetic state. Assuming not much goes into thermal or chemical or acoustic or elastic, assuming I'm pretty much getting a trade-off of potential for kinetic, it'll reach its maximum speed at its lowest spot. And then it'll trade that back up into potential. So it's going to be going fast here. It's going to swing up here, and it'll go up. And it will go up to the same height it was over here because I can't create or destroy energy. Energy is conserved. Whatever it had there, it's going to go into here, and then it's going to go back up again. And once it's traded kinetic back into potential, it should be at the same height. And here's where I really, really trust it, is that's then going to get converted back into kinetic. And then it should come back to the same spot here. So let's see. If I were to put my face in the way, which I'm going to do right now, I trust physics enough to know that as long as I don't add energy, and I have to be careful there, because if I gave it a push, that's me converting my breakfast into energy, and that's me metabolizing and giving more energy than it started with. I don't want to do that. But if I just let it go, it should just come right back to where it started. Let's try it. And let's see. I haven't done this in a while. I may flinch. I may not trust physics as much as I like. So right now, if you try this is so scary because this. Okay, I trust it. That is really scary. Does someone want to try that? It's really scary. We have like 2 minutes left. I'll let someone try it if you want. But so here I am. I've been doing physics long enough. I really do trust physics. And even though I'm not touching anymore, so I'm sure no one's doing work. Like that first push, I was a little nervous that I actually gave it a little push. Even though I now know no one's doing work on it, just watching a bowling ball go to your face is quite scary. But so right now, if there's no energy being taken out of the system, I'm going to get constant height every time. So it's going to get back up to here, and then it's going to go kinetic, potential, kinetic, and then it's going to get up to here again. Now, what's going to eventually happen, it's already starting to happen, is I am getting a very slow bleed out of energy. Now, I can't lose energy. Give me one more minute, like one more minute. I'm going to stop at 48. I cannot create nor destroy energy. Energy is not leaving the system. So energy has to be going somewhere. And if this slowly swings to a stop, I have to wonder where it went. I look through my list. That thing is running into air molecules its whole way. And every time it bumps into an air molecule, it speeds that air molecule up. It gives it a little nudge. One definition of molecular kinetic energy is temperature. So we're actually warming up the room right now. When that eventually slows to a stop, the room will be a microkelvin higher than it was a second ago. All right, let's call it a day.